Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 8.4 titled Mathematical Induction. Alright, this and the next two sections, 8.5 and 8.6, are going to be very important. We're actually going to be introduced here to another method of proving something. Right? We had a whole chapter on proofs before, chapter 2. Where we saw, direct proofs, proofs by exhaustion, proof by cases, proof by contrapositive, proof by contradiction, all sorts of proof techniques. This is just another one. This principle of mathematical induction is used to prove statements about the integers. Usually the positive integers. Usually it's to prove statements about integers that are greater than or equal to a certain integer. So from some certain integer onward. So let's take a look. You can read that title, that opening paragraph. All right, so the two components of an inductive proof. The base case establishes that the theorem is true for the first value in the sequence. So they're talking about genies granting you wishes on days and whatnot. Then the inductive step establishes that if the theorem is true for some integer k, then the theorem also holds for k plus 1. So we're going to have a statement about integers, typically again the positive integers. Most of our statements in this section here, because it's an introduction, most of the statements will be about the positive integers. And if we want to prove that a statement is true for all positive integers, we need to show first that it's true for when n is 1. We have to show it's true in the base case when the value of the integer is 1, and then we'll show what's called the inductive step. We'll show that if the statement is true for n equals k, then it must be true for n equals k plus 1. All right, and that'll tell us that, oh, well, hey, we showed it was true for 1 earlier, then it must be true for 1 plus 1, or 2. And if it must be true for 2, then it must be true for 3. And if it must be true for 3, then it must be true for 4, and then for 5, and then for 6. So do you see how that causes a domino effect that shows the statement is true for all positive integers? So I'm going to reread this here. So this is called the principle of mathematical induction. It states that if the base case, right, for when n equals 1 is true, and the inductive step is true, then whatever statement we're looking at, whatever theorem we're looking at, holds for all positive integers. So again here, suppose Sn is some statement parameterized by a positive integer n, so n represents a positive integer. Then Sn, S of n, is true for all positive integers n if S of 1 is true, right, so it's true for n equals 1, and then we can show that if S of k is true, then S of k plus 1 is true. And if you can show this, then, since it was true for 1, this will tell me that, oh, it must be true for 2 then, and oh, if it's true for 2, it must be true for 3. If it's true for 3, it must be true for 4, and so on. So it's true for all positive integers. Right, now this inductive step, showing that, S of k implies S of k plus 1, you're going to prove this, directly. This is a if-then statement. This is a conditional statement. And remember, how do you prove a if-then? You assume the hypothesis is true and then show the conclusion, right, through some series of steps. So the inductive step is a compact way to state that an infinite sequence of implications are true. Again, Sk for all k in the positive integers, Sk implies Sk plus 1. This is what I was saying earlier. Implies that, is the same thing, has the same meaning that, S1 implies S2, and S2 implies S3, and S3 implies S4, and. And since we've shown S of 1 is true, then all these other things fall into place. In the statement Sk implies S of k plus 1 of the inductive step, the supposition that S of k is true is called the inductive hypothesis. So, remember, when you're trying to prove P implies Q, or if P then Q, you assume P is true, and then, through a series of steps lead to Q. This is going back to chapter 2. So what we're assuming to be true here, that S of k is true, that the statement is true for some integer k, that's called the inductive hypothesis. And then we're going to, through a series of steps, show that indeed S must be true for the next integer up. S must be also true for k plus 1. Alright, so again, they show you the animation here. Start it, right? So, see, P of 1 is true. And then you've shown that for all k greater than 1, for all positive integers, P of k implies P of k plus 1 is true. So, for k equals 1, if you've shown this is true, that I've said this several times now, this implies that P of 2 is true. So P of 1 and P of 2 are now true. And since you've shown that P of k implies P of k plus 1, then when k is 2, P of 2 implies P of 3 is true. So P of 3 must also be true. And then that implies that P of 4 is true. So it must be true for 4 as well. And then for 5, and then for 6, and then for 7, and for 8, and for 9, and so on, and so forth. Right? So the statement is true for all positive integers, right? For all n greater than or equal to 1. I hope this makes sense. And I hope it'll make more sense, when we actually look at an example. All right. So first, I'll go through these participation activities with the multiple choices and whatnot, and we'll go through their example of an inductive proof, and then I'll write out my own. All right, I'll do several examples of an inductive proof here, and the next 2 sections are on all inductive proofs. So theorem, for all n belonging to the positive integers, for all positive integers, Q of n is true, where Q of n is a statement that is parameterized by a positive integer n. All right. In an inductive proof of the theorem, what must be proven in the base case? Right? So what's the base of all the positive integers? That's 1. You have to show that first it's true for n equals 1. And then, in an inductive proof of this, whatever theorem you're looking at, what must be proven in the inductive step? You must prove that for all positive integers k, Q of k will imply that Q of k plus 1 is also true. So if Q of k is true, then Q of k plus 1, the next one down the line, is also true. And then if the inductive step says that for all positive integers, Q of k implies Q of k plus 1, what's the inductive hypothesis? What's the hypothesis of this if-then statement? What are you going to assume is true? It's that Q of k. And then you're going to, assuming that's true, show Q of k plus 1 is also true. All right, so here they're going to break it down. This next part of the section, they're breaking down a proof one step at a time here, taking it very easy. Very nice introduction to a proof by induction. So the next example will be a proof that for any positive integer n, the following equality is true. So for any integer n, and this statement involving n is called P of n. They're calling this statement P of n. The sum from j equals 1 to n of terms called j is equal to n times n plus 1 divided by 2. So if n is assigned a particular value, then the values of both sides of the equation are determined. Right? For example, if n is 5, then P of 5 would be the sum from j equals 1 to 5 of j, and that should be equal to 5 times 5 plus 1 over 2. That should be equal to 15. And you can verify that. 1 plus 2, this left side would be 1 plus 2 plus 3 plus 4 plus 5. And that is equal to 15. So P of 5 is true. The left side of the equation, like I said, would be 1 plus 2 plus 3 plus 4 plus 5. The right side would be 15. So the assertion that the equality holds for a particular n can be denoted by the predicate p of n, right? So the statement p of n may be true or false depending on the value of n, right? It is a predicate. This is going back to chapter 1 now, right? All right, so we're defining the predicate p of n to be this statement. The theorem is for every positive integer n, right? So for all n greater than or equal to 1 that are integers, this statement is true. We're trying to prove that. Now, again, we're not writing the proof yet. They're just trying to get you familiar here with the predicates. So express the statement p of 3. So let's replace n with 3. So this the left side would be the sum from j equals 1 to 3 of j, which should just be 1 plus 2 plus 3. So it's either this one or this one. And the right side, plugging in 3 for n, would be 3 times 3 plus 1 over 2. So it's this expression here. This is the value, the statement p of 3. The theorem states that for every positive integer n, p of n is true. In a proof of this, in an inductive proof of this theorem, what would be proven for the base case, right? The base case is when n equals 1. You know, if it's a statement about all the positive integers, right, you'd be starting at 1. So the base case, when n equals 1, this left side is just the sum from j equals 1 to 1 of j. So just the number 1 equals 1 times 1 plus 1 over 2. So that's this here, right? From j equals 1 to 1, which would just be the number 1, equals 1 times 1. So when n equals 1, that's your base case. Here, they're saying, again, the same predicate. What is p of k plus 1? So just go through, just like any other predicate, I'm going through the predicate p and replacing all the n's with k plus 1. So this left side would be the sum from j equals 1 to k plus 1 of j's. And this right side would be k plus 1 times k plus 2, right? K plus 1 divided by 2. So that's this here. And in an inductive proof, again, if we're trying, and I'll get to the proof of this in a second. I'll write this out on some paper. In an inductive proof of the theorem, what would be proven in the inductive step? So you'd show the base case, show it's true for n equals 1, and then you'd show that for all positive integers k, if p of k is true, then p of k plus 1 must also be true. So you'd say for any integer k greater than or equal to 1, if p of k is true, now p of k is just replace m with k, that's this statement, then p of k plus 1, oh, that's not p of k plus 1, this is p of k plus 1. So here it is. For any integer, any positive integer, k greater than or equal to 1, if p of k is true, then p of k plus 1 is true. That's what you're trying to show. And if you've shown that and you've shown the base case, then all those dominoes fall into play, right? 1 is true implies it's true for 2, implies it's true for 3, implies it's true for 4, it's true for 5, it's true for 6, and forever and ever for all positive integers. All right, so let me show you the proof. So I'm going to write this theorem out, and we are going to prove it. Now, again, this is usually for statements involving an infinite set of integers that's bounded below. Right, that's from some integer upward. Typically, those types of statements, those types of universal statements, will be proven by mathematical induction. Okay. So again, for every positive integer n, the sum from j equals 1 to n of these j terms will be equal to n times n plus 1 over 2. So here I'm going to write, this is proof. And this is a proof by induction on n, the value of n. Now you could go through and start looking at, when n equals 1, is it true? When n equals 2, is it true? And I'll do that actually on some separate paper. I mean, you can go through some examples and see if you actually believe this. So this is not the proof. This is not the proof. Not proof. These are just examples. Remember, a few examples does not prove a for every statement, a universal statement. But when n equals 1, you have the sum from j equals 1 to 1 of j equals 1 times 1 plus 1 divided by 2. Is this true? Well, the left side would just be the number 1. The right side's 1 times 2 divided by 2. That's equal to 1 as well. So yeah, it's true for n equals 1. Is it true for n equals 2? So just replacing n with 2 up here, we have the sum from j equals 1 to 2 of j equals 2 times 2 plus 1 divided by 2. Well, the left side is just 1 plus 2, right, if I write out the sum. And the right side would be 3. And yeah, we get 3 equals 3. That works. Again, I could do this forever. This doesn't prove anything. I'm just trying to feel like, do I believe this statement? And after just a couple examples, I'm like, I feel like I believe that this is true. But again, just showing a few examples is not a proof. All right, so now that I feel that it's true, I go back and we'll perform this proof by mathematical induction on the value of n. So first, the base case. The base case. So when n equals 1, right, when n equals 1, the base of the positive integers, or the first of the positive integers. Now I've already written this, so we know it's true. Right? The sum from j equals 1 to 1 of the j's there, is that equal to 1 times 1 plus 1 divided by 2. The left side is 1, the right side is 1, so the statement is true. So the statement is true for n equals 1. Great. Again, not a proof. This is only the beginning of the proof, the base case. Next comes the inductive step. We're going to show, I want to show that if this statement is true, or show that for all integers k, for all integers k, right, some generic integer, not just the integer 1, for all integers k greater than or equal to 1, right, because again we're dealing with the positive integers here, right, so I can't use negative k or anything like that. Show that for all positive integers k, if this statement is true for k, so if the statement is true for n equals k, so from the sum from j equals 1 to n equals k of j equals k times k plus 1 divided by 2, if this is true, then the statement will also be true for when n equals k plus 1. So now I go through here and replace n with k plus 1. So sum equals j equals 1 to k plus 1 of the j's equals, now n is k plus 1, so this is k plus 1 now instead of n, and this is k plus 1 plus 1, so k plus 2 instead of n plus 1, and then divided by 2. We have to prove this now. And this is just like proving any other if-then statement. So off to the side here, recall that if you're proving, right, to prove if P then Q, you first assume P is true. Right, you assume P is true and then lead to Q. Right, we're going to do a direct proof. So this assumption, right, So we're going to assume that this is true, that the statement is true when n equals k. And then we're going to show that that leads us to the fact that it's true when n equals k plus 1, right, the next integer up. So we're going to assume that the sum from j equals 1 to k of j is equal to k times k plus 1 divided by 2. And then this assumption, right, this assumption that I just made, this is what they're calling the inductive hypothesis, right? This is the hypothesis of this if-then statement. Now, I wish to show that it's true, that this statement's true, that k plus 1, when n equals k plus 1. So if I'm trying to show that it's true, I can't start with it. I can't start with this equation. But we can start with one of the sides. Remember back in like trigonometry, you know, when you tried to show that a certain trigonometric identity was true, you started with one side and transformed it into the other. Same thing here. All right. So if I'm trying to show that the statement is true for n equals k plus 1, I'll start with one side and show that it's equal to the other. Right, we'll eventually, you know, using our hypothesis at some point, using what we're assuming to be true, this inductive hypothesis at some point. So I'm going to start with that left side, the sum from j equals 1 to k plus 1 of the j's. Again, don't say that it's equal to this. I don't know that yet. We're going to show that this sum is equal to k plus 1 times k plus 2 over 2. And that'll show that the statement is true when n equals k plus 1. All right. Now, if you recall from section 8.3, there was a skill that was learned there, a skill that was shown about removing the final term, pulling out the final term. Because we're going to have to use our inductive hypothesis at some point, right? We're going to have to use the fact that the statement is true for k at some point. Now this inductive hypothesis, right, involves the sum from 1 to k, not to k plus 1. So what I want to do here is rewrite this so that we have a sum involved from 1 to k. Well, if I want to go from 1 to k, that's just going to mean I need to get rid of that last term. So remember, this is equivalent to the sum from j equals 1 to k of the j's, right? The same exact sum, but then plus that final term, plus k plus 1. All right, aren't these equivalent? These are the same. And that was that removing the final term. Now, here's where the inductive hypothesis comes in. We have assumed that this sum is equal to k times k plus 1 divided by 2. So I will write this. And then, you know, by the induction hypothesis, this is equal to, you know, this sum from j equals 1 to k of j is equal to k times k plus 1 divided by 2. And then don't forget we saw that final term that we removed, that we pulled out. So then we have plus the k plus 1. All right. And what I eventually want to get, I want to transform this, you know, using some algebra into the right side of my statement here, right? The statement we're trying to show. So let's see what happens when I put these together. I need a common denominator. So I'm going to take this this k plus 1 over 1, I'm going to multiply by 2 over 2, right, to get a common denominator of 2. And then we have k times k plus 1 plus, 2 times k plus 1 all over 2, right? The common denominator of 2. And then, oh, look at that. These two terms in the numerator have a common factor of k plus 1. I pull that out. We have k plus 1 times k plus 2. That would be left over when I remove k plus 1 over 2. Hey, that is what I wanted to show it be, that it was equal to. Okay, I wanted to show that this sum from j equals 1 to k plus 1 of j's was k plus 1 times k plus 2 over 2. So we have just shown, and I'll write it in words. So we have just shown that, if the statement is true for n equals k, then it is also true for n equals k plus 1. And since we showed it was true for n equals 1, right, that base case, right, since we showed it was true, since we showed this original statement was true for n equals 1, since it's true for n equals 1, then it must be true for n equals 2. And since it's true for n equals 2, then it must be true for n equals 3. And since it's true for n equals 3, it must be true for n equals 4, and then 5, and then 6, and then 7, and so on and so forth. So we have just proven, therefore, we have just proven that the statement is true for all positive integers. The sum from j equals 1 to n of j is equal to n times n plus 1 divided by 2 for all positive integers n. And I'm done. The proof is over. I put a little block or a QED or something. Because again, we showed it was true for n equals 1. Then we showed that if it's true for k, then it will be true for k plus 1. And then, since we showed that, again, because we showed it was true for 1, that gives us 2, then 3, then 4, then 5, then 6, then 7, then 8, and then forever. All positive integers. This is an example of a proof by mathematical induction. And again, this type of method of proof is usually reserved for when we're proving statements, universal statements involving a set of integers, either all positive integers or integers from one value upward, where that first value is the base case, and then we prove if it's true for this, then it's true for the one above it. Right? If it's true for k, then it's true for k plus 1. And then starting from that base case, oh, that must mean all these ones after the base case are true forever and ever and ever. Right. Okay. All right, so let me get to another one. That's just one example. We'll do plenty over the next several sections. So they go through the same kind of thing I did there, right? See, they pull out that last term, say, hey, use the inductive hypothesis. This sum is equal to k times k plus 1 over 2, and then this is equal to k plus 2 times k plus 1 over 2, which is what we were trying to show. They even have another video on it if you want to watch. If you want to watch them do it, go ahead. Now, as I mentioned, the base case isn't always 1. Sometimes you want to prove a statement's true for all integers greater than 3 or 5. So sometimes the smallest n for which some statement of n holds is some constant c other than 1. Then the base case must show that s of c is true, right? Whatever the lowest integer is, the integer that you're starting at. The inductive step will still be the same thing. You prove that if s of k is true, then s of k plus 1 is true. But instead of for all values of k greater than or equal to 1, it's for all values of k greater than or equal to that lowest integer, right? Greater than or equal to whatever c is for the base case. And inductive proof assumes that s of k and k greater than or equal to c are true. and uses those two facts to establish that S of k plus 1 is true, right? You have your inductive hypothesis and show that the statement is true for one integer higher. All right, so I'll show you here. All right, I'll write this out. Here we have an inequality. So again, notice, now this time it's not for all positive integers. It's just for the integers greater than or equal to 4. All right, it's just for the integers greater than or equal to 4. So the base case here is not when n is 1. It's going to be when n is 4. So the proof is, again, since it's a statement about integers greater than or equal to a certain integer, right, from one integer up, from 4 up, a good method here would be to try to do a proof by induction. So again, we're going to do a proof by induction on the value of n. Right? By induction on n. All right, now before I get to the proof, again, I want to believe this. I want to feel like I believe that this is true by showing myself a few examples. So again, this is not the proof. This is just a few examples. So starting with n equal, for any as n greater than or equal to 4. So starting with n equals 4, we have 2 to the 4. Is 2 to the 4th greater than or equal to 3 times 4? All right, replacing them with 4 here. Well, this left side's 16. This right side's 12. That is true, yeah. How about when n is 5? You'd have 32 is greater than or equal to 15. Yeah. When n is 6, you'd have 64 is greater than or equal to 18. Of course. I mean, this left side, it's an exponential expression. This right side's a linear expression. So, it's definitely going to be growing much, much faster, that left side. So I believe that this is true for all n greater than or equal to 4. But like I said before, showing a few examples is not a proof. Just makes me believe it, that's all. So now let's get into the proof. Now if I'm doing induction on n, we start with a base case. Now the base case this time is, when n equals 4. So when n equals 4, plug it in, I'm writing it again. 2 to the 4th, is that greater than or equal to 3 times 4? So that's, 16 is greater than or equal to 12. Yes, the statement is true. When n equals 4. Now comes the inductive step, the main part of the proof. We're going to try to show that for all integers k greater than or equal to 4, right, starting with our base case here, for all integers k greater than or equal to 4, if the statement is true for k, for n equals k, so if 2 to the k is greater than or equal to 3 times k, this is our inductive hypothesis, show that then the statement will also be true for when n equals k plus 1. So 2 to the n equals, k plus 1. So 2 to the k plus 1, show that that's greater than, 3 times the quantity k plus 1. Or, 3k plus 3, 2 to the k plus 1 is greater than or equal to 3k plus 3. Same thing. Show either one of these things and you got it. All right. So again, we're going to assume this hypothesis and then show the conclusion. Again, you can't start with this. You have to start with one side and show it's greater than or equal to the other side, or start with the right side and show that it's less than or equal to the left side. But you can't start with the inequality. You have to show the inequality from one side to the other. So I'm going to start off by assuming that that k is greater than or equal to 4, and 2 to the k is greater than or equal to 3 times k. This is our induction hypothesis. The things that we are assuming to be true in this inductive step. Now, if I'm trying to show that 2 to the k plus 1 is greater than or equal to 3 times k plus 1, again, you can't start with this, or 3k plus 3. Got to start with one side and go through some steps to show the other. So I'll start with 2 to the k plus 1. I'll start with the left side. So say I start with the expression 2 to the k plus 1. Now I want to eventually use my induction hypothesis. I want to use this fact that we have assumed to be true. Now the fact that we are assuming to be true involves 2 to the k, not 2 to the k plus 1. So how can I express this so that we have a 2 to the k instead of a 2 to the k plus 1? Well, this will be involved, use some properties of exponents here, some algebra. 2 to the k plus 1 is equivalent to 2 times 2 to the k, isn't it? 2 to the first times 2 to the k is 2 to the k plus 1. And then here's where the inductive hypothesis is going to be applied. Right here, see this 2 to the k showing up. So by the inductive hypothesis, this 2, I'm just taking this down here. This 2 times 2 to the k, well, 2 to the k we know is greater than or equal to 3k. So that means 2 times 2 to the k would be greater than or equal to 2 times 3k. Right? That's just taking this inequality we're assuming and multiplying both sides by 2. Right. Now, how am I going to turn this into this? Well, let's see. Now 2 times 3 to the k. Now this is involving a sum, not a product of 3k. It's 3k plus something. 2 times 3 to the k is, if you write it as a sum, that's 3k plus 3k. Right? That's 2 times 3 to the k. Here we go. And we can also use this part of our, we know that we are assuming that this is true for some k that's greater than or equal to our base case, greater than or equal to 4. And since k is some number greater than or equal to 4, it's definitely greater than 1, isn't it? And then multiplying by 3, that would imply that 3k is greater than 3. So this 3k plus 3k that I've got here must be greater, and then using this here, sorry, this is a bad proof. I should have, this is a bad organization. It's not a bad proof, it's just bad organization. Using this fact here, this 3k plus 3k, just one of the 3k, the second 3k here is greater than 3. So this is greater than 3k plus 3, which is equal to 3 times k plus 1. Or I could have just left it as 3k plus 3 like I had up here. I wanted 3k plus 3 on the other side. So what we have shown, what we have just shown, I started with, I started with 2 to the k plus 1, and we have shown through all this, using the inductive hypothesis and stuff, and the fact that k is greater than 1, we have shown that 2 to the k plus 1 must be greater than or equal to 3 times k plus 1. So we have used the fact that the statement's true for k to show that the statement is true, right? To show that this statement is true when n equals k plus 1. And then, since we showed the base case, we showed it was true when n is 4, this implies that it's then true when n is 5. And then that would imply it's true when n is 6, when n is 7, when n is 8, and so on. So putting these together, we have just shown inductively that 2 to the n is greater than or equal to 3n for all integers greater than or equal to 4, right? N greater than or equal to 4. And I'm done with the proof. So that was a little trickier because it involved inequalities, but still, you got to know what you're using, know what you're assuming true in this inductive step. What's your inductive hypothesis? And then look at what the statement looks like when n is k plus 1, and start with one side. Use your induction hypothesis. Use the things that are true to try to make sure that try to show that the other is greater than or equal to or whatever it is on the other side, whatever you're trying to show. And if you've got the base case true, and then if it's true for k, then it's true for k plus 1, that base case sets off a domino effect that shows it's true for all integers greater than that base case value. So again, some tricky stuff, maybe the first time you're seeing it. Oh yeah, another video if you want to watch that here. Maybe they'll explain it better than I did, I don't know. Oh, they use basically the same reasoning I did. Alright, so watch the video here if you want. Alright, so let's go through this step by step here. And this is the last part. So, hey, consider a proof of the following fact. For all n greater than or equal to 4, 2 to the nth is going to be greater than or equal to n squared. So the base case here, remember, would be at the integer 4. Alright, the base case would just be what happens when n equals 4. Is that true? And it would be, right? 2 to the 4th is 16. 4 squared is 16. They're equal, right? So 16 is greater than or equal to 16. So it's true for 4. And then for the inductive step, you're going to try to prove that for any integer k, greater than or equal to 4, if 2 to the k is greater than or equal to k squared, then 2 to the k plus 1 will be greater than or equal to k plus 1 squared. Right? So for every k greater than or equal to 4, if the statement is true for k, then the statement will be true for k plus 1. And then below is an argument for the inductive step. In which line is the inductive hypothesis used? The inductive hypothesis would be the if part. You'd be assuming that, first of all, k is greater than or equal to 4, but you'd be assuming that 2 to the k is greater than or equal to k squared. So that's used right here from line 1 to line 2. Now in line 1 they just did a simple algebra property of exponents like I did. 2 to the k plus 1 is 2 times 2 to the k. And you see how 2 to the k got replaced with k squared all of a sudden, and there's a greater than or equal to. They're using the inductive hypothesis here. Right? 2 to the k is greater than or equal to k squared. So it's used in line 2. Right, and then if you follow the rest of the reasoning, this is k squared plus k squared. And since k is greater than or equal to 4, I can replace one of these k's in the k squared with 4, and it's greater than or equal to k squared plus 4k. And then they replace, 4k is 2k plus 2k, so these are equal. And then again, since k is greater than or equal to 4, 2k is definitely going to be greater than 1. So this is greater than 1. I mean, if you're greater than, you're greater than or equal to, right? And then k squared plus 2k plus 1 is equal to k plus 1 squared. So you've shown that, they've shown here that 2 to the k plus 1 is greater than or equal to k plus 1 squared. So if 2 to the k is greater than k squared, then 2 to the k plus 1 is greater than or equal to k plus 1 squared. If it's true for k, then it's true for k plus 1. They've proven that inductive stuff. And if you proved, and we said the base case where n equals 4 was true earlier, so therefore there you've shown it. You've shown that all this statement is true for all values 4 or greater, all integers 4 or greater. A lot of stuff. All right. So you are asked to do that here for certain sums. Prove each of the following statements by induction. There's a lot of statements involving sums here, some products. I don't think I assigned all of them, but even if I didn't, try to do them all. Try to do them all. Get some more practice, and hopefully get better at this stuff. Here's more inequality, proofs by induction for some inequalities. Probably a little trickier than the sums. And that's it. But again, I don't think I assigned all these on your assignment 8. But still try to do them all, though. Try to practice them all. And if you have any questions, let me know. And of course, you can look at the solutions to check your work. Please try to do them, though. Try to do them ahead of time. Try to work them out, the proofs by induction, before you look at how they did it. Because if you're just copying down solutions, you're not going to go anywhere. You're not going to learn anything. All right, so hopefully this helps you when you're going through this on your own. If you have any questions, of course, let me know. And thank you very much for watching.